This is going to be homework 5 part A, in which we derive the Gibbs phase rule, and then we'll go on to kind of explain what it means in a situation at the triple point and where water and vapor coexist. So we'll start off with a system with the vapor, the liquid A, and the liquid B, and the total Gibbs energy of this system can be represented by N times G, and the chemical potential of this can be represented as UI, or a chemical potential of each individual phase can be represented as UI times D and G over D and then NI. And this is important because at a constant temperature and pressure, and I is not equal to J, we can say that UI of liquid A is equal to the UI of liquid beta, which is also equal to the UI of our vapor phase. This will be important later on. So the next thing we'll do is we'll move on to figure out how many different variables that we could be working with in a situation like this. So each phase can have its own number of mole fractions. So the vapor phase could, for example, be 50-50, or it could be 4 parts made up of 0.25 each. The important part is it adds up to 1. So we'll start with each phase. We have our P, and that can have a total number of different mole fractions that's equal to C. However, because we know that all of the mole fractions together add up to 1, this is actually C minus 1. And then the other things that can be changed are temperature and pressure, so that will add on 2. That is our number of variables. So the next thing we can figure out is how many different equations we have. So our number of equations, number of EQs, is equal to, so it will be equal to our different phases we have, because these are all equal to each other, so that would be equal to this would be equal to that. However, because of this relationship, this is not an individual relationship with the very last term, so all the in-between steps would have 1, but the last one would not. So again, we'll get our P minus 1, and then times our mole fractions that we have will give us the number of different equations that we could solve for. So if we subtract these from one another to find out our degrees of freedom, or how much we're able to change, we get P times C minus 1 plus 2 minus P minus 1 times C, which gives us so the PC's will cancel out, and then we get our plus C. So we end up with C minus P plus 2. And this is our number of different mole fractions and our phase, number of different phases. So for water at its triple point, we would only have water itself, so H2O, and that would be a 1. And since it's at the triple point, it would exist as ice, gas, and a liquid. So we have 3 phases and plus 2, which would equal 0, meaning we have 0 degrees of freedom. What that means is that we are unable to change the mole fractions the pressure or the temperature, because changing this would mean that water would no longer be at the triple point, which is why we have no degrees of freedom if we would like to have pure water at the triple point. But if we were to go along on our pressure temperature graph here, if we were to go along this line at which water exists as a liquid and a vapor, along this line we would have our same, just water, minus our two different phases, liquid and vapor, no solid this time, plus 2 once again, giving us a total of 1. Now this means we have 1 degree of freedom, meaning we are able to change something without completely ruining everything we want. So if we were to say we want our temperature to be at this point, we can no longer choose our pressure because we only have 1 degree of freedom, meaning if we choose our temperature, the pressure is set, and if we choose our pressure, the temperature would also be set. If we move on to a situation in which we have water and ethanol, we now have 2 different components which could be in different phases. So we have a 2 here for our C, and at a point where these both exist as a vapor and a liquid, we would have 2 different phases again, and plus 2, which gives us 2 degrees of freedom. And because we have 2 degrees of freedom, you might think that you can now change the pressure and the temperature without having any repercussions, but that would not be true, because as you remember, part of our variables was the mole fractions themselves, meaning you could either set a temperature and a mole fraction, which would determine the pressure and the other mole fraction. You could set the pressure or temperature and the pressure, which would set both mole fractions, or you could set the pressure and mole fraction, which would end up setting temperature and the other mole fraction. As you can see, you were able to determine 2 things. However, once those 2 things, degrees of freedom, were determined, the other variables in this equation were set. All right.